The topic of this lecture is regularization. So in overfitting problem, this regularization is the most widely used method against overfitting. So what is regularization in the first place? Its goal is to discourage complex models, or in other words, it makes your model simpler, okay? That's the goal. And then why do we make our model simple? Okay, we already mentioned this issue earlier in other lecture, like Occam's razor. So in Occam's razor, actually we prefer a simple model over complex model. Then why do we prefer a simple model? The reason is if you compare simple model over a complex model, so let's say complex model may show better performance in training data, but most likely this simple model will show better performance in future test data. Okay, that's why we prefer a simple model. So, and that's the goal of regularization, make your model simpler. So regularization is actually you're gonna make your model simpler, and or in other words, you measure the complexity of a model and reduce the complexity of a model. That's what this regularization does. The next question is, how do we measure the complexity of model? We already covered this issue in Vichy dimension lecture. So in this Vichy dimension lecture, we compared the Vichy dimension and the number of parameters as the estimate of the complexity of model. And I said the Vichy dimension is better measure. Okay, it's better estimate for estimating the complexity of model than number of parameters. So, but in practice, in real machine learning method, it's very difficult to use Vichy dimension in regularization. The reason is, number one, in most of machine learning algorithm, it is very difficult to compute the Vichy dimension of that particular algorithm. That's the first reason. And second reason is, even though we know the Vichy dimension of the algorithm, the test error, the boundary of test error by using SRM or structural risk minimization, the boundary of this test error by using SRM is too pessimistic. Pessimistic means this boundary is too big. Okay, so because of these two reasons, it's very difficult to use Vichy dimension as the measure of complexity of model. Okay, so that's why we don't use Vichy dimension in real regularization. Okay, so instead you may use number of parameters, or we're gonna reduce the value of parameters, etc. Okay, these are we're gonna study in this chapter. By the way, if you are not familiar with this Vichy dimension and the structural risk minimization and the boundary of test error, you can take a look at the Vichy dimension lecture. So anyway, this regularization is very important topic in machine learning in general. Let's see how the regularization is implemented in machine learning algorithm. You can use a regularization technique in gradient method. So in gradient method, the first step you do is
to define error function, right? So let's say here you have your error function JW, that's your error function or loss function. Then if you use a regularization method, you have another term here saying lambda times RW. So lambda is constant, it's called regularization constant, and you have RW. That's called a regularization term. And what is RW? So RW actually represents the complexity of model. Okay, you have your own method, whatever, algorithm. And this RW represents the complexity of model. This shows how complex your model is. Okay, that's RW. So in your gradient descent method now, instead of minimizing error function only, you actually minimize this whole thing. So you minimize error function, and also at the same time you minimize this term, regularization term. So this is constant. So that means you minimize the complexity of model as well. That's the basic idea of this regularization method. So you minimize your error, and also at the same time you minimize the complexity of your model. You make your model simpler. Okay. So this constant lambda is constant, and if this value goes up, okay, then you give more emphasis on this regularization term, so that makes your model much simpler. If you reduce this value, you put more focus on error, so your model is a little more complex. You emphasize in reducing error. So that's the role of this constant lambda. So if lambda is very high, if value goes up, it reduces the values of W, and it reduces variance, makes model simpler. Okay, then another question is, then what is RW? I said RW is it represents the complexity of model. Then the next question is, then how do we represent the complexity of model? There are many choices, okay, you can choose from. So in regularization technique, these two methods are famous, okay. So again, the question is, how do you define this RW? In other words, how do you represent the complexity of model? The first choice is called L1 or Lasso regularization. Here, this RW is represented as the summation of the absolute value of parameters. Okay, and the second choice is called L2 or rich regularization, and here this RW is defined as the summation of the square values of parameters. Okay, so you may wonder what this means. I'm going to explain this too in more detail next slide. So anyway, RW represents the complexity of model, and there are two famous approaches to define this RW, and the first one is L1 and second one is L2. So in regularization method, you add another term to the error function and you minimize the whole thing together. And that's the basic idea of regularization method. So that another term it represents the complexity of model. So basically you minimize error, and also at the same time you minimize the complexity of model. So when you use a regularization method, actually what happens is you are minimizing the value of parameters very small or zero. Let me repeat. when you use a regularization method, you are making the values of parameters very small or zero. Okay, so if you make the value of parameters zero, it's called L1 regularization. If you make the value of parameters very small, it's called L2 regularization. Then you may wonder why making the value of parameters small is related to reducing complexity of model. Yeah, let me explain it. The first case, suppose this regularization method makes the value of parameters zero. It makes sense actually. Okay, so some parameters, some unnecessary parameters are actually removed, because by using regularization method, the value of parameter is zero. Okay, that means we don't care about those parameters. So some parameters are gone. The number of parameters in your model is reduced. So that definitely makes your model simpler. So that makes sense. And second case, this regularization method makes the value of parameter very small. The why is this related to the complexity of your model? The reason is, it's described here. So if the weights in deep learning, the parameter is weight in network, right? So if the parameter values are large, then in gradient descent, the weight values are very high. Then a small the derivative is also high. So a small change in feature can result in a large change in the update. Okay, so we don't like it. So if you remember in learning rate, if learning rate is too high, it has problem with the converging to the answer. So if the weight values are too high, the gradient is high, and its variance is too high. So it's no good. So you have to keep the weight values very small. So in that case, weight value is small means the derivative is small. So it's you update your weights gradually in a small scale. Okay, that's much better. So that's why this the small value of parameters are preferred in learning. So finally, let's in next slide. How do we encourage small weights? How do you penalize large weight in a more theoretical way? So now let's talk about the first regularization method called L1 regularization, or Lasso regularization. In L1, this RW term is defined as follows. So RW term is the summation of the absolute value of weight. That's RW. So the error function is added by lambda times this RW, summation of the absolute value of W. So that's L1 or Lasso regularization method. So if you use this method, what happens is many value of W actually becomes zero. And this means this reduces the number of parameters, because many parameters become zero. That means you automatically remove some unnecessary features. So that's what happens if you use L1 regularization technique. So in some sense, the feature selection is done automatically if you use L1 method. So again, this lambda is called weight decay. This determines how dominant regularization is during gradient computing. So if you emphasize this part, we emphasize in reducing the complexity of model. You increase this lambda value, then your model becomes simpler. That means many of parameters actually become 0. If this value is small, actually you focus more on minimizing error, then in that case, well, less number of parameters will be 0. So the L1, if you use L1, this term is not differentiable, as you can see here. So you have to use some other approximation method. If you use L1 regularization, there are actually multiple solutions of this. Okay, some W's are 0, but this set is not unique. Okay, so it generates multiple solutions. In one case, one particular set of W's are 0. In other cases, the other set of W's will be 0. Second regularization method is L2, or rich regularization. In L2, the R term is given as follows. So RW is summation of the square of W parameter. So this is the final error function. So error function plus lambda times the summation of square of W. So as you can see, we minimize this term together. So it minimizes error, and also it minimizes this. Because this is square, if the W value is high, because it's square form, it gives a lot of penalty to a high value of W. So that's why this L2 minimizes the value of W. So if the value is big, it gives big penalty to big weight, mainly because this is square form. And here, unlike the L1, this W value is not becomes 0. Okay, it becomes small value, but not 0. So pretty much every parameter remains. Okay. And unlike L1, it generates unique solutions. So if you use L2, it generates one final unique set of W values. In L1, it removes some parameters, but the sets to remove is not unique. Okay, so but in L2, it generates unique set of W values, so its answer is unique. Sometimes people combine these two L1, L2 method together, and it's called elastic regularization or elastic net regularization. So as you can see here, this is a combination of L1 and L2 method. So error function, this is L1, this is L2, or this is L1 and L2. In this case, the addition of these two are 1. Okay. So anyway, sometimes this method is known to be better than L1 or L2, but not always. Okay, so this is more study on whether this actually is better than L1 or L2. There's some disadvantage of this method is computationally expensive. As you can see here, with a lot of computation needed here. So it's slow. It's computationally expensive and slow. And this is not a proper method for small size data. So your data is small. It is not recommended to use this elastic regularization because it has more parameters than L1 or L2. So this is not a good choice to use elastic method in small size data. I said the regularization method is used in gradient method. So let's say you use L1 or L2 method in your problem. Then how do you use in a gradient descent method? Actually, these are pretty much same. The only difference here is the error function has changed. So in ordinary gradient descent, you have error function only. But if you use L1 or L2 regularization, you have another term, RW. So depending on L1 or L2, it can be summation of W or square value, summation of square value of W. Okay. So the error function is changed. That's the only difference. And the rest is exactly same. And because the error function is changed, you change the derivative of this part, right? So that's the only change between ordinary gradient descent and gradient descent with regularization term. So in the case of L2 regularization, you have to take derivative of these things. So without this, okay, without this, this one is the ordinary gradient descent method, this error function, right? And if you use L2, error function is defined as like this, right? So you take derivative of this part. That's the only difference. Okay, the rest is exactly same. You keep update weight using this formula. So finally, if you use L2, this is the update rule. So you take derivative of this one, and this becomes this. Okay. And if you use L1, this is the update rule for L1. In L2, I put, lambda is divided by 2. This is, so for simplicity, if you differentiate this, 2 comes in front. So to make the formula simple, you put lambda is divided by 2. It's a trivial thing. And in L1 case, it is this formula, the L1 form, the summation of absolute value of W is not differentiable. So people sometimes use this one as an approximation. Okay, so derivative of J plus derivative of L1 form, but it's not differentiable. So instead, if people use sine of W as the derivative form, it's kind of approximation. So anyway, you change the error function, and based on error function, you have this update rule, and just keep updating your parameter, just like you did in the gradient descent. So far, we have seen the L1 and L2 regularization. This slide is a little advanced stuff. So here, this is the L1 regularization form. Okay, if you take a look at another form saying this minimum error function subject to this. If you have seen the lecture of SVM, SVM uses constraint optimization. So in constraint optimization method, we transform this original problem into Lagrangian form. So in this case, suppose this is the original problem, then if you use a constraint optimization method, this whole problem is transformed to a Lagrangian form like this. So this one, equation 1, formula 1 is Lagrangian form of formula 2. Okay. So in constraint optimization method, so we have two formula. The formula 1 is Lagrangian form of formula 2, and this one has its own answer, and this one has its own answer. Their answer is not necessarily same. Okay, sometimes their answers are different, but there are cases where these answers are exactly same. That is when what is called the KKT conditions are satisfied. So these two answers are originally different, okay? But when a certain condition is true, their answers are same, okay? That condition is called KKT condition. In this particular case, the condition is this. So if this condition is true, these two answers are same, right? So this is L1 regularization form. So if this is true, the answer of this and this answer of this are exactly same. So let's take a look at a more specific example here. So we have, let's say we have two parameters, W and W2. So we're going to minimize this error function subject to this, like this, L1 form. So in this case, W1 plus W2 is less than S. Then I said this answer of this is exactly same as this one, only when KKT condition is true. So we can assume this is true. This is true. This is KKT conditions. We can assume this condition is true, right? Because that's the only case when the answer of this and answer of this is same, okay? So this is true. Then if you look carefully, so the addition of W1 and W2 is 0. Both are positive, okay? So the addition of these are limited, constant S. So to satisfy this, there are a couple of options, okay? The first option is, you make all these weights smaller, okay? So we have many attributes. This is just two. We have like hundreds of parameters, and their addition is limited, like constant. Then in that case, you have to make every weight very tiny, small, okay? It's very difficult actually. So on the other hand, what actually happened is some of the parameter is become 0, okay? So in this case, let's say this is become 0 and this becomes S. So we have a lot of W values, like 100 of them, 100 of parameter, and the estimation is like S. What happened is actually many of the W values become 0, okay? So that's what happens. That's why in L1, many parameters actually become 0, okay? I'm going to explain this using in a more visual way. Okay, in this case, this is the shape of error function J, suppose, okay? It can be any arbitrary shape. So let's say this is an error function of J. And this is the shape of L1 term, okay? L1 term here. Makes sense. This is linear, okay? This is L1 form, and this is error shape J, okay? So when I said KKT condition is true, that means these two conditions touch each other at some point. That's when these conditions are true, okay? So if you look at this picture, this can, this J is in any arbitrary shape, and it move around and touch the surface of this L1 space, right? Then most likely it's gonna touch the edge of this shape. You think about it, you visualize it, okay? You have very complex error surface. It moves around and touches this space. Yeah, it is not. It is possible sometimes this error surface touches this area, but it's very much likely touches the edge of this surface, right? So it touches this edge of this edges here. That means this error KKT condition is true, and that's, people look carefully, this one here, it touches this edge, W1 is 0. If it touches this edge, W2 is 0, etc. Okay, so that's why in L1 many parameters actually 0, because this error surface touches corner edge of the surface of L1 term. So now this is the case of L2 regularization. So again, as I said in previous slide, this is L2 form. And if you think about this form, okay, then again, this one here, the L2 form is Lagrangian form of this problem. Okay, again, I don't want to go over the detail of this process. So anyway, this is Lagrangian form of this form, and again, the answer of this and answer of this may be different, but there are cases where these two answers are exactly same. The cases are when this KKT condition is true. So in this case, the KKT condition is this, okay? This equals S, okay? This equals S, okay? So solution happens, in this case, solution happens when this is S, okay? So what happened in L2 is actually you're gonna calculate the W value and each value of W should satisfy this. So if you look at this picture here, the shape of this L2 form, this one, is a circle, okay? L1 is this rectangular form, okay? In L2, this is the shape of circle here, okay? And again, we have error surface, any random arbitrary error surface in J error function, okay? And this is the shape of L2 form here. So again, KKT condition means these two surfaces touch each other at some point, okay? In L1, most likely it touches edge of this L1 shape, okay? That's why many parameters 0 actually. But in L2 case, it's a circle, okay? So it can touch anywhere, okay? It doesn't necessarily touch any, this one corner here. Not really, okay? You can touch anywhere here, okay? So that's why, it's this the parameter of this W1, W2 not becomes 0, okay? So it can be small, but it not necessarily 0, okay? That's why this L2 makes parameters very small, but not necessarily 0. Okay. So we have seen the case of L1 regularization and L2 regularization. Actually, we have something called P norm. This is P norm form. So the term RW actually is represented as this. So if P is 1, this becomes L1, because P is 1, then this becomes this. And if P is 2, it becomes L2, okay? So if P becomes any integer number, okay? So if you can keep going, P can be any one, right? So it's called the P norm and LP. But in most cases, we use L1 or L2, but you can assume there are other forms, L3, L4, LP, even we have L infinity, okay? So anyway, this is the general form of the regularization term. Again, we usually use L1 or L2, but there are many other forms, okay? So this picture shows the shape of P norm. So if P is 1, this is L1 form, right? So this L1 form looks like the square. We have seen this picture in previous slide. If P is 2, okay, and that it's a circle, okay, it's a circle. T is 2, it's a circle. You can increase the P value, okay, you can, this is shape of P equals 3, etc. Okay, so it can be any number, okay, P is like, sometimes it can even be infinite, okay. P is infinite, actually what happened is you choose maximum value of parameters, okay. So anyway, we use L1 or L2, okay, and how about P is 3 or 4, 5, etc. Actually, not many people tried this, okay. We heavily use L1 or L2, but not many people have tried using L3, L4, L5, etc. Okay, so you need more study on this one. But anyway, usually we use L1 or L2. You may wonder if P can be smaller than 1, like P equals 0.5. Its shape look like this. Okay. And the problem is, If p is less than 1, the problem is I'm gonna talk about this one first. Okay, so if p is greater than 1, okay, 1, 2, 3, 4. Okay, we look at the shape. The shape is convex. This is very important actually. So if p is 1 or greater than 1, it's the shape of p norm is convex. Okay, but if p value is less than 1, it looks like this, and it is not convex anymore. Okay, that causes problem. Okay, so if you add this term to error function, okay, error function is convex. Let's say error function is convex, and then if you add another convex function, the whole thing is convex. That is good. Okay, we can use gradient descent. But if you add another term RW, and this is not convex, well, do have a problem. The error function is convex. This is not convex. Well, it's very problem is tricky. Okay. So if p is less than 1, this form is not convex anymore. It causes problem. Okay. So we don't use p norm where p is less than 1. Okay. Anyway, if p becomes higher, it gives more penalty to large weight. Okay. But on the other hand, if the p value is small, like p equals 1, it actually generates very sparse parameters. Okay. And large values of p actually discourage large weights. So p value is very high. It gives a lot of penalty, very big penalty to large weights. So in previous slide, I talked about the convexity of functions, so the convexity of R term. Okay, so here I'm going to give a little reminder of convexity of function. This kind of reminder. So this one shows the definition of convexity. So let's say we have function f, and you choose two arbitrary point in the function. Let's say here, and you draw a line between these two points. The definition of convex is, so every point in this line is above the value of function here. Okay, so every data in this line is above the value in this function. Okay, so that's the definition of convex. So mathematically speaking, this is definition of a convex. So this function is convex if this is true. So this one represents every point in line connecting these 2 points. Okay. So the x1 is this point, x2 is this point. So x1, x2. So this one means every data in this line. Okay. And this one here is every data along these functions. Okay. So every data in this line is greater than or equal to the value in this function. Okay. So that's the definition of convex. Okay. This reminder of a convex function. So earlier, when I talked about the p norms, if p value is 1 or greater than 1, the p norms are convex. So that's what it says here. But if the p value is less than 1, I said this is not convex anymore. Okay, so that causes some problem. So the point I'm trying to make in this slide is, so in general, if we have two functions f and g, and let's say f is convex function and g is another convex function, then the addition of these two, f plus g, is also convex function. That's the theorem. So in our gradient descent with regularization method, let's say error function is convex, okay, and the p norm L1 or L2 is convex. Then the addition of these two, error function plus the regularization term, is also convex. That's a huge advantage. We can use gradient descent on a convex function. It's guaranteed to find a global answer, right? So But on the other hand, if the phenom is the p-value is less than 1, that makes this regularization term non-convex, then it causes problem. We have studied SVM algorithm in different lecture, in different chapter. In this slide, we're going to take a look at this SVM method in a different angle. So this one here is the definition of the primal problem of SVM. So we maximize margin under these conditions. Okay, so that's definition of primal problem of SVM. And we replace this part by hinge laws. So the basic difference here is in hinge, if you use hinge laws, actually if correction is correct, it returns 0, error is 0. And if the prediction is wrong, this error size of error is proportional to the value of this. Okay, that's the basic idea of using hinge laws. So it gives more penalty in wrong prediction. This prediction is incorrect. Okay. So anyway, this is now it's changed to this one using hinge laws. So the only difference between these two is this part is replaced by hinge laws, meaning we give more penalty in wrong answer. And if you look at this, both are minimizing. Okay, we're gonna minimize both. So why you just combine them together and minimize the whole thing? That's what happened here. So this one comes here, and this one comes here, and we put some constant for every data. Let's say Ci. Then this formula is, if you look carefully, this formula is the Lagrangian form of SVM. If you remember the SVM, this is the Lagrangian form of SVM using hinge laws. It's exactly the same. Okay. So in this case, this is error function actually. Okay, this is error function with hinge laws, right? And this is L2 regularization. So actually the SVM is actually, if you explain SVM in terms of regularization, SVM is actually algorithm which minimize hinge laws with L2 regularization. That's actually SVM method.